So evaluate this where our region is x squared plus y squared less than or equal to 16. So that is the cylinder of radius 4, centered on the z-axis. X bigger than 0, y less than 0, and z between -1 and 1. So where b is equal to, so x squared plus y squared less than or equal to 16, x bigger than or equal to 0, y less than or equal to 0, and -1 less than or equal to z less than or equal to 1. So x squared plus y squared less than or equal to 4. So y less than 0. So it's over here, this thing. So here is the cylinder of radius 4, and we are inside of that. So certainly we want to use cylindrical coordinates. This is the x-axis, y-axis. Oh, I'm sorry, -1. So z is between -1 and 1, so it actually goes down here. So that's 4 on the x-axis, -4 on the y-axis, -1 to 1 on the z-axis. Okay, so how would we describe, certainly we want to use cylindrical coordinates, and how would we describe this in cylindrical coordinates? Right? So we want to describe the region in the xy plane with polar coordinates, and then just -1 is less than or equal to z, less than or equal to 1. So the region in the xy plane in polar coordinates is how? It's just a, polar rectangle, right? So x bigger than 0, y less than 0, so it's this. All right, so how do we describe that? Well, r goes from 0 to 4, and then theta goes from pi to 3 pi over 2. Okay? So, just a sector of a cylinder, essentially, and it's described very nicely in cylindrical coordinates. So triple integral over b of x z squared dv is equal to, so first z, -1 to 1, and then r and theta, 0 to 4, and then pi to 3 pi over 2, xz squared dz, and then r dr d theta. So the z is done in rectangular coordinates, essentially. The iterated integral, the first step, the z step, is in terms of just rectangular coordinates. And then you have a double iterated integral, and that's done in polar coordinates. So cylindrical coordinates is really not much different than polar coordinates. Okay, so first with respect to z, so antiderivative with respect to z is 1/3 z to the third times x. So we got pi to 3 pi over 2, 0 to 4, and then 1/3 x z to the third from z equals -1 to z equals 1, r dr d theta. So from -1 to 1, z to the third is 2. So this is 2/3 x. So 0 to 4, 0 to 3 pi over 2. 2/3 x r dr d theta. So now after that step, you want to transform x and y into r and theta. So after doing the dz, now transform x, y to r and theta. Okay, so the x is r cosine theta, and that does the trick for you. So 0 to 3 pi over 2, 0 to 4. So this is 2/3 r squared cosine of theta dr d theta. Okay, so antiderivative with, 0 but pi here. Antiderivative with regard to r, 2/9 r to the third. Two-ninths r to the third cosine theta from r equals 0 to r equals 4 d theta. So 4 to the third is 64, and at 0 it's 0. 64 times 2, 128. So we've got 128 over 9 integral from pi to 3 pi over 2 cosine of theta d theta. Antiderivative cosine is minus sine from pi to 3 pi over 2. So, 129, 128. 128 over 9, and at 3 pi over 2, it's negative 1, so this is 1 minus 0. So 128 over 9 is the final answer there. All right. 245. So we want to evaluate e to the square root x squared plus y squared over, I've got a little typo here. Well, there's just a missing less than or equal to sign there, I think. Right. Oh no, that's not a typo. They just should have put the square root 3 to the left of the y. Let's draw. So we have x squared plus y squared, which is the radius, right, between 1 and 4. So between circles of radius 1 and circles of radius 4. So evaluate e to the x squared plus y squared dv over b, where b is not minus 1, 1 less than or equal to x squared plus y squared less than or equal to 4. And then y less than 0 again. And then what was the deal with the x? I had this funny thing here. X less than y times root 3. So x less than, so 1 over root 3x is less than y. I'll write it that way. And z is between 2 and 3. So I'm just, so the z is just bounded by constants. So I'm just going to draw the bit in the xy plane. All right, right? So we have the circle of radius 1, the circle of radius 2. The line y equals 1 over root 3x. So this is the line y equals 1 over root 3x. So y less than 0, x less than the line. So we're talking inside here. Okay, what is the angle of this line? What is this angle here? How do you get the angle of a line through the origin in polar coordinates? Right, the slope of this line, so we'll call this angle theta here. The slope of this line is 1 over root 3, right, which is equal to the rise over the run, right, which is equal to, like, one of the y coordinates over x, which is equal to, right, r sine theta and r cosine theta, which is tangent of theta, right? So the slope is, so this angle that goes with the slope, 1 over root 3, is tangent of theta, right? So what angle in the first quadrant gives you tangent equal to 1 over root 3? Sine over cosine. One of those special angles again, right? 0, 30, 60, 45, 90. So one of those just very, limited special angles that we've got. I know some other ones, but they're less used. All right, which special angle is that? It's pi over 6, right? Sine over cosine. Sine is 1/2, cosine root 3 over 2, right? These cancel and you get 1 over root 3. Okay? So that angle there is pi over 6. So how can we describe now the entire region, right, which is essentially this band? I don't even want to. I mean, z is between 2 and 3. So you just take this bit in the xy plane, and you take the z coordinates between 2 and 3, and you get this, half of a cylindrical shell there. Right. So described in terms of polar coordinates, theta goes from pi over 6 all the way to pi plus pi over 6. Right, because this is pi over 6 as well. And so pi over 6 and pi over 6, so that's pi over 6 and 7 pi over 6. And then r goes from 1 to 2, and z goes from 2 to 3. Right, so the triple integral over b of e to the square root x squared plus y squared dv is, well, first you do z from 2 to 3, and then r, 1 to 2, and then theta, pi over 6 to 7 pi over 6. And so this is e to the r. So x squared plus y squared is r squared. Square root is r. We don't have to worry about like positive r or negative r because r is already positive, right? We're only dealing, with positive values of r here. R going from 1 to 2. dz r dr d theta. Okay, so do the antiderivative in terms of z first. Right, so in cylindrical coordinates, z is independent of r and theta. Right, so r and theta are constants with respect to z, because z does not depend on them and they don't depend on z. They're independent of each other. So from 2 to 3 for z, it's just 1. So the antiderivative with regard to z is just the r e to the r times z, and times that interval of length 1, so it's just 1. So not much to calculate there. R e to the r dr d theta. All right, well, antiderivative of r e to the r. How's that one? How do you deal with that one? All right, that one you have to use integration by parts, right? I'm going to do it off to the side here, and I'll just save a little space. So u is the polynomial x, dv is e to the x, du is dx, and v is e to the x. So it's x e to the x minus antiderivative e to the x. So this is x e to the x minus e to the x. So x minus 1 e to the x. Okay, so just to keep the main calculation more coherent here. So pi over 6 to 7 pi over 6, x minus, or not x, sorry, r minus 1 e to the r from 1 to 2 d theta. R goes from 1 to r goes to 2. So this is, well, at 2, this is e squared. And at 1, it's 0. So it's just e squared, which is a constant. Right? So this is pi times e squared. It's a constant, so the integral is just that constant times the length of the interval, which is pi. So pi times e squared. The odd numbered problems are listed in the back of the book. I guess we can take a quick look there. Pi e squared over 6. Hold up there. Pi e squared over 6. Oh, I know what it is. Y has got to be less than 0, so it's this. The y coordinate needs to be less than 0, so just this bit here. X is 1 over root 3. X is less than y. Oh, so it's not that. It's this over here. Right, the x coordinate is less than the y coordinate. The y coordinate is the greater one when you're above the line, not below the line. Oops. So it's this, actually. So the theta is pi to pi over 6. Pi to 7 pi over 6. So pi to 7 pi over 6. Pi to 7 pi over 6. Pi to 7 pi over 6. So pi e squared over 6. Okay. Next is 250. In the following exercises, the boundaries of the solid E are given in cylindrical coordinates. Express the region E in cylindrical coordinates. Convert the integral to cylindrical coordinates. E is the, I see. So write E in terms of cylindrical, the using inequalities. They don't quite give you the inequalities here in 250. So E is the outside of the circular cylinder, R equals cosine theta, above the xy plane, and inside the sphere, r squared plus z squared is 9. So r equals cosine theta in the xy plane is this. We've talked about that one a few times. Right, that's the circle of radius 1 centered at 1/2. For theta, minus pi over 2 less than or equal to theta less than or equal to pi over 2. Because at pi over 2, minus pi over 2, the angle is down here, and this is 0. Right? And then as you go from 0 to pi over 2, or from minus pi over 2 to 0 to pi over 2, the radii get smaller and smaller like that and go down to 0. So that's that circle, right? And then we're talking about that cylinder above the xy plane and inside the sphere of radius 3. Right, so we got r squared plus z squared equals 9. So that's just x squared plus y squared plus z squared equals 9. So it's just some cap there. This is kind of some weird kind of thing here. There we go. That's a nice picture. Something like that. Okay. So, so how does this go? So, describe this in terms of cylindrical coordinates. Right? Start with theta, and then r, and then z. Right? So first theta needs to be bounded by constants. Well, they're right here. Minus pi over 2 less than or equal to theta less than or equal to pi over 2. And then r, well, these red lines are bounded. How? The radii are bounded by what?
Zero and cosine theta.
Right. And then z bounded how? You start at the xy plane, then you go up to that sphere.
It would just be 0 to z in terms of the rewritten.
Yeah. 9 minus r squared square root. Or you can put 9 minus x squared plus y, x squared minus y squared. That would be fine if you wanted to. After you do the integral for dz, then x and y get turned into r and theta at that point. So you can do it on the boundaries ahead of time or not. Doesn't matter, whatever's easier. So this is E. And then they don't actually give you an integral, just write just in terms of some f. So triple integral over E of f x y z dv is the triple iterated integral 0 to square root 9 minus r squared, 0 to cosine, that's ugly, isn't it? 0 to square root 9 minus r squared, 0 to cosine of theta, and then minus pi over 2 to pi over 2. F of x, y, z, f of r cosine theta, r sine theta, z, if you want. I mean, it's just quibbling around. dz, r, dr, d theta. You don't have to change to r and theta until you've evaluated the dz. After you evaluate the dz, then you go in terms of r and theta. Okay. So that's a nice region. I mean, what would be an interesting? Probably you could just find the volume of that region would be nice. Yeah. Yeah, like just finding the volume of that region would be interesting enough, and it would turn out to be a U substitution at the dr step. But then you're going to have this cosine business here. So you have 9 minus cosine squared. No, that's no good. No, you couldn't do it. Cosine 9 minus. Yeah, because see, 9 minus cosine squared, right? You'd end up with this. That's no. If you had 9 minus 9 cosine squared, then you're in business, because then you can just change it into 9 sine squared. 9 sine squared theta, right? And which is just going to be 3 sine theta. Like when you do those trigonometric substitutions thing, but that's not what you're going to have. You're going to have this. So that's not. And then you have a cosine theta out here. No, because that's gonna go away when you do the integrate. It's gonna be like this. Yeah, you couldn't just find the volume because we don't know how to do the antiderivative of that in terms of theta. Yeah, you'd end up with this. Not doable, sadly. Don't know what function you could actually put there. If you put a y, no, that'll mess it up. That'll mess it up. Yeah, I don't know. I don't think there's too many functions there that you could actually get an integral that you could find antiderivatives of. This is the whole sort of contrived scenario in calculus classes. I mean, you have all these problems, these integration problems, and you keep doing them using the fundamental theorem of calculus, which assumes you can find an antiderivative. But most functions you just can't. I mean, they just don't have nice antiderivatives. Functions with nice antiderivatives are hard to come by, and most functions just don't have them. So, and my coffee cup's got a crack in it and it's leaking. That's just a bummer. Coffee all over my desk, and I can't find the antiderivative. It's just so sad. All right. So it was 250, 258. In the following exercises, find the volume of the solid whose boundaries are given in rectangular coordinates. So E is below the plane, z equal to 1, and inside the parabola, z equals x squared plus y squared. That's a pretty easy one. So you've got that paraboloid z equals x squared plus y squared, and then this horizontal plane z equals 1. So the horizontal plane, z equals 1. So what is the intersection of this paraboloid with that plane? So this is the paraboloid z equals x squared plus y squared. So the intersection of the plane z equal to 1 and the paraboloid z equal to x squared plus y squared is described by, well, you have the two expressions for z. So it's described by 1 equals x squared plus y squared, right, which is the circle of radius 1. Right, so we want to find the volume inside the paraboloid under the plane. So the solid inside the paraboloid and under the plane is, well, it's just the circle of radius 1. So you have 0 less than or equal to theta less than or equal to 2 pi. 0 less than or equal to r less than or equal to 1. And then what about z? Well, z is bounded up top by 1, and it's bounded below by what? Bounded below by the parabola. Right, so bounded up top by the 1, bounded below by this, the paraboloid. So what do I put down here on the left?
X squared plus y squared.
Yeah, x squared plus y squared, or r squared if you want. Right. So the volume of E is the triple integral over E of 1 dV, which we would do in cylindrical coordinates. So r squared to 1, 0 to 1, 0 to 2 pi, dz r dr d theta. So there's nothing here, it's just a constant, so you get 1 minus r squared. One minus r squared, and then you have this r dr d theta. So that's r minus r to the third dr d theta. Antiderivative with regard to r is 1/2 r squared minus 1/4 r to the fourth from 0 to 1. So that's 1/2 minus 1/4, and then minus 0, so that's just 1/4. That's just a constant, so it's 2 pi times 1/4, so pi over 2. All right, real easy, that one. Um, 262. Again, we're finding the volume of the solid. So E is located inside the sphere, x squared plus y squared plus z squared equals 1, above the xy plane and inside the circular cone z equals square root x squared plus y squared. So here, we've got the cone z equals square root x squared plus y squared underneath the sphere of radius 1. Right? So what you need to know is, to describe this region in cylindrical coordinates, what you need to know is, what is this intersection? Right? Where do these guys intersect? You know, and what is this region in the xy plane when you reflect it down or project it down into the xy plane? Okay, so, well, obviously it's a circle of some sort. Obviously a circle of some sort. So you combine the equations in what way you can to eliminate the z. So combine equations to eliminate z, and thus see which x, y define the intersection of the two surfaces. Right, so we have one surface is the cone, the other surface is the sphere, and we're interested in where those guys meet. Right, so the surface is given by an equation in x, y, and z. The other surface is given by an equation in x, y, and z. If you can combine those equations and eliminate z, then you're in business. Okay, well, here you just have an expression for z. Z is equal to square root x squared plus y squared. So you got x squared plus y squared plus z equals 1. Right, so I have 2x squared plus y squared equals 1. So x squared plus y squared equals 1/2, which is the circle of radius 1 over the square root of 2. Right, centered at the origin. So to describe this region in cylindrical coordinates, right, theta, r, and z. Well, the theta is making a full rotation around, so 0 to 2 pi, obviously. What about the r? Well, the x and y, right, the x and y are defined by this disk, you know, the circle of radius 1 over root 2. So you're going from 0 to 1 over root 2. And then the z, well, it's caught between the cone on the bottom and the sphere on the top. So that's z equals 1 minus x squared minus y squared. Right, so this is that region E. Right, inside the cone and under the sphere. Right, so if you want this last equation, I mean, you're going to have to change it into r and thetas later. So, I mean, you could do it now if you want. It might save some space. This is just r, and this is square root 1 minus r squared. Okay, so the volume of E is the triple integral over E of 1 dV. So it is the triple integral from r to square root 1 minus r squared, 0 to 1 over root 2, and then 0 to 2 pi. dz r dr d theta. So antiderivative, well, there's no z here, it's just 1, so it's just the difference of these two boundaries on the interval. So we have square roots 1 minus r squared minus r. And then don't forget about that conversion factor, right? R dr d theta. Okay, so distribute through 0 to 1 over root 2, 0 to 2 pi. So that's r times, I'm going to write it like this, 1 minus r squared to the 1/2 minus r squared dr d theta. So to do the antiderivative here, you do a u substitution. So let u equal 1 minus r squared, and then you would, cancel out this r, and you'd have u to the 1/2. So I'm just going to guess at it. I think it is, what is it? So 1 minus r squared to the 3/2. Oops, forget this. 0 to 2 pi. 0 to, I'm doing the r now. So 1 minus r squared to the 3/2. I think it's negative 2/3. Is that right? Negative 2/3. 1 minus r squared to the 3/2. I think it's 1/3. Because now when you take the derivative of this, it's negative 3, yeah? Right, because we take the derivative here, no, 1/3. It's going to be 3/2 times 1/3 times minus 2. Because you're going to use the chain rule there. Then you're going to have the negative here, and that, yeah, that's right. And then you get, so that's the antiderivative. But, if you don't want to just guess at it, you can do the u substitution. So this is from r equals 0 to r equals 1 over root 2, and then d theta. So, at 1 over root 2, this becomes a half. So 1 minus a half is a half. So 1/2 to the 3/2 square root of 8. No. 1/2 to the 3/2. That's 1 over root 2 to the 3rd. So 1 over square root 8. Minus 1 over root 2 is 1/3 times 1 over root 8. Minus, at 0, so minus minus is plus. At 0, it's 1/3. Plus, at 0, that's 0. D theta. So that is what do we got here? So minus 2 over 3 root 8 plus 1/3, and that's negative, isn't it? That can't be negative. Zero to 1 over root 2. Oh no, no, the bottom here is large. So this is, so what do we got here? This is root 8 over 3, so root 8 minus 2 over 3 root 8. That's because the square root of 8 is bigger than 2. So root 8 minus 2 over 3 root 8 is, of course, a constant. All that times 2 pi. And so that's the volume of that that solid underneath the, 1 minus underneath the sphere and above the cone. Well, this is interesting. That surface could also be done, that surface, that solid can also be described in terms of spherical coordinates. And I have root 2 minus 1 over root 2. I have a different answer for that. It should be the same answer, of course. So again, the derivative here is 3 halves. So minus 1 half times 2r minus 2r gives me r 1 minus r to 1 half minus 1/3 r squared. And the boundaries we have here are from the cone to the sphere. So cone, so that's r to square root 1 minus r squared, 0 to 1 over root 2. That is correct. And 0 to 2 pi. Oh, so this is 2 pi over 3 root 8. Oh, no, they're the same. It just looks different. Because if I distribute the root, yeah, it's 1 minus 2 over root 8. 2 over root 8 is 1 over root 2. No, it's the same. Interesting. Interesting problem. So let's take a look at that in terms of spherical coordinates. So that region, so let's redo it. That's a good one. Let's redo this. So without the red, we don't need that in this case. It's more naturally described in terms of spherical coordinates. So we can also describe this region in spherical coordinates, mainly because, like, the cone, the side of the cone is exactly the line of slope 1, because you get exactly 45 degrees there. Right, so that's the line of slope 1, so you get exactly 45 degrees, and then the rho, the spherical radius, is, of course, 1. Right, so in terms of rho, theta, and phi, so the rho is from 0 to 1. The theta, well, that's going in a full circle for theta, 0 to 2 pi. And then the phi, it just goes from 0 to pi over 4. The angle of declination, 0 less than or equal to phi, is less than or equal to pi over 4, 45 degrees. So that, that ice cream cone shape there has a real nice description in terms of spherical coordinates. So now the volume of E is the triple integral of E over E of 1 dV. Putting that in spherical coordinates. So in what order do you often do spherical coordinates? I usually do rho, theta, phi. So 0 to 1 for rho, 0 to 2 pi for theta, and then 0 to pi over 4 for phi. And then there's the conversion factor, right? So that conversion factor for spherical coordinates is more like, I don't know, complicated than, more intricate than the one for polar coordinates, right? It's this rho squared sine phi, and that had to do with calculating the volume of that spherical box that we talked about in the lecture. So then this is d rho, d theta, d phi. Okay, so antiderivative with respect to rho squared is 1/3 rho to the third. And then the sine phi, of course, is constant. So 1/3 rho to the third sine phi. There's two ways to write phi, by the way. There's this, and then there's this, which is a little bit easier handwriting-wise. This is like a typewriter font, and this is the handwriting font. So that's from rho equals 0, or no, from rho equals 0 to rho equals 1. You just got to be careful that phi doesn't look like a rho. So it's just 1/3. So I'm just going to pull that, and then d theta, d phi. So I'm just going to pull that 1/3 out front. So 0 to 2 pi, 0 to pi over 4, sine phi, d theta, d phi. There's no thetas. It's all just a constant with regard to theta, so it's just 2 pi out here. All right, so the whole thing is just, the integral is just the constant times the length of the interval, which is 2 pi. So 2 pi over 3, 0 to pi over 4, sine phi d phi, which is equal to 2 pi over 3, antiderivative is minus cosine phi, from 0 to pi over 4. So that's 1 minus 1 over root 2. Right, same answer as before. Although not immediately, but I'll show you how. Got to do a little bit of, so this is root 8 over root 8 minus 2 over root 8 times 2 pi over 3. So this is 1 minus, well, root 8 is 2 root 2. Right, 2 root 2. So that's 1 times 1 minus 1 over root 2 times 2 pi over 3. Yeah. So that's pretty neat, right? I mean, we described that region in two different ways, in cylindrical coordinates and in spherical coordinates. Did the calculation, got the same answer. That's nice stuff. All right. Now, if you were doing an integral that was more complicated, I mean, here we were just doing the triple integral of 1, but I wish I had an example. I don't. There could be a function, x, y, z, that when you convert it to cylindrical coordinates, you can't solve, but you can do it with cylindrical coordinates. Or spherical coordinates, or the other way around. Something you can't do in spherical, but you could do in cylindrical. So depending on what the function is, one might be preferable to the other. But if you could do both, then it gives you a check on the calculation. All right, so that was 262, 270. Oops, where's my mouse? 270. We need some spherical stuff. So in the following exercise, evaluate the triple integral over b. So triple integral of 1 minus square root x squared plus y squared plus z squared. And so we got x squared plus y squared plus z squared, which is rho less than 9. Y is bigger than 0. Z is bigger than 0. And x is whatever, I guess. That's not what they have drawn here. I think they mean x bigger than 0 as well. I think they mean y, but yeah, they mean x. So oh no, they don't. Yeah, this is the x-axis. This is the x-axis here going forward and backward. The y-axis is going across. So they have them reversed. So x is going from, so here's 0 and x going from -3 to 3. Okay, so they've got triple integral over e. What was it again? 1 minus x squared plus y squared plus z squared dv over e, where e is given by, well, x squared plus y squared plus z squared less than or equal to 9. So that just translates to 0 less than or equal to rho less than or equal to 3. Because rho is x squared plus y squared plus rho squared is x squared plus y squared plus z squared. And then y is bigger than or equal to 0, and z is bigger than or equal to 0. So inside the sphere of radius 3, and so I guess I will draw the x-axis here this time, and the y-axis here like they do in that picture. So I guess that's the whole upper hemisphere, yeah? No, it's a sort of a quarter of it. It's a quarter, like an orange slice. Right, so like if you sectioned an orange into 4s. Okay, so this is 0 less than or equal to rho less than or equal to 3. What about theta? So theta is going this way in this picture. Right? This is theta equal to 0 right here. Is the x-axis going all the way to the negative x-axis. Right, so theta is going from 0 to pi. And then the phi is going where? What about the phi? What's the angle of declination? Right, phi is going from the positive z-axis down to here. Right, so that's pi over 2. So then 0 less than or equal to phi less than or equal to pi over 2. So 90 degrees. Remember, phi is between 0 and 180 in describing spherical coordinates. Right, latitude, right, latitude and longitude, right, they go in, the full range is 180 degrees. 90 degrees south is the South Pole, 90 degrees north is the North Pole. So that's minus 90 to 90 is 180. But in spherical coordinates, we go from 0 as the North Pole to 180 as the South Pole. Just a different way of doing it. Although you could do it the other way. Now with the conversion factor would be different because you'd be using negative values of theta, or for phi. Alrighty, so this is equal to the triple integral. So typically we do rho, theta, and phi. One minus, so x squared plus y squared plus z squared is rho squared. and then it's rho squared sine phi, that conversion factor, d rho d theta d phi. All right, so we've got, let's clean up the expression a little bit. Or not 2 pi, pi over 2. 0 to pi, and then 0 to 3 for rho. So that's rho squared minus rho to the third sine phi d rho d theta d phi. So 0 to pi over 2 0 to pi, and then antiderivative for rho, 1/3 rho to the third minus 1/4 rho to the fourth, from rho equals 0 to rho equals 3 d theta d phi. So this is equal to, so at 3, this is 9. Minus 81 over 4, which is a negative number, which is fine, d theta d phi. And of course at 0, this is 0. Oh, I lost my sign somewhere. Where'd that go? Sine phi d theta d phi. We're doing the antiderivative with respect to rho, and of course the phi is constant, so it's just, you know, the antiderivative of this with respect to rho times the constant, which is sine phi. So 81 or so, 36, well, I'll figure that out later. Sine phi d theta d phi. Alrighty, so let's see, 36 minus 81, 5, 45. So minus 45 over 4. Zero to pi over 2. 0 to pi sine phi d theta d phi. No thetas, right? So just a constant here with regard to theta. So it's just the constant times the length of the interval, which is pi. So you get minus 45 pi over 4. Integral from 0 to pi over 2 sine phi d phi. So we've got minus 45 pi over 4 minus cosine phi, antiderivative, from 0 to pi over 2. So at pi over 2 it's 0, and at 0 it's 1, so it's just 1 there. So minus 45 pi over 4. Okay, so that's the integral of that function over this region. I think this function actually sort of makes some sense in terms of, well, no, if it was 3 minus square root x squared plus y squared plus z squared, it might make a little more sense physically. Sort of that the density on the outside is 0 and the density in the middle is 3. So here the density on the outside is -2 and the density on the inside is 1. At the origin is 1. So as you move inward, you get more dense. So some sort of negative density towards the outside, and as you move in, so this is like the radius of the sphere, right? So as you move in along the radius, the density becomes 0 and then 1 at the origin. So if you started with a 3 here, it would kind of make a little more sense. It'd give you a strictly positive function. All right. $258. 272. What did I do? Oh, backwards. No, I just did 272. That was 270. Now 272. All right. So f of x, y, z is z, and b is bounded above by the half sphere, x squared plus y squared plus z squared equals 16, with z bigger than or equal to 0, and below by the cone, 2z squared is x squared plus y squared. All right, so we've got this cone. So 2z squared equals x squared plus y squared. So that's a cone. And x squared plus y squared plus z squared equals 16. So that's the sphere, radius 4. So the region that we're looking at here, again, is this thing above the cone, so inside the cone, and below the sphere. So again, this snow cone region, although it's a little different this time. So this is a 4 up here. So to describe this, so again, you can do this in terms of cylindrical coordinates. It would be fine. To describe this here, we need, in terms of spherical coordinates, we need to know what the angle here is. What's this angle? Right? So if this is the x-axis, y-axis, z-axis, what is this line here in the yz plane? So in the yz plane, right, 2z squared equals x squared plus y squared becomes 2z squared equals y squared. So z is equal to 1 over root 2 y. Right, so this slope here is 1 over root 2. Right, so what would the angle be? Well, actually, hold on. Root 2. Well, that is not one of the special angles now, is it? It certainly is not. One would need to yeah, I don't think that that's what they mean. I think they mean it's got to be a typo. It's got to be a typo. I think they mean to put a 3 here. Right? I think they mean to put a 3. So in the book it says 2. Z squared. Okay, but I mean, you can do it in terms of cylindrical coordinates, and in my notes here I did it in cylindrical coordinates, but it's messy in that too, because finding the intersection of the cone and the sphere leads you to some kind of wacky looking numbers as well. Just does not quite work out nicely. So I think he means 3. And why that's important is because this becomes 1 over root 3, right? And tangent theta equals 1 over root 3 when theta equals what? Which theta gives you that? Right? Again, it's sine over cosine, so it's pi over 6. All right, so I think that's what he means. So this region, so it's more, I made a skinny cone. It's more of a flat cone, actually. It's more of a flattened out cone. So more of a doggy cone than one of those, those water cups, those cone-shaped water cups. So this region is described in terms of spherical coordinates. So the rho goes all the way out to that sphere. Right? I mean, so the rho, the radius goes all the way out to the sphere. Right? So rho is just between 0 and 4. So I think the dudes that wrote this book, they did the solutions to the odd-numbered problems and the even-numbered problems. They just threw them in there and didn't actually work them out. And then theta, this was doing a full rotation for theta, so 0 to 2 pi. And then the phi, right? So the phi is going from here to here, so that's 5 pi, or no, not 5 pi over 6. Pi over 2 is 3 pi over 6, that's 2 pi. Pi over 2 is 3 pi over 6. So 3 pi over 6, so it's 2 pi over 6. Pi over 3. Oh, duh, of course. That's 60 degrees. This is 30 degrees. 30 plus 60 is 90. Right, so that's the description in terms of spherical coordinates. So now they're asking you to calculate the triple integral over E. I guess it's E. Triple integral over E of Z dV. So this is the triple integral over E. So 0 to pi over for rho, theta, and phi. 0 to 4 for rho. 0 to 2 pi for theta. And then 0 to pi over 3 for phi. Z, so remember the conversion. So x is rho sine theta cosine theta sine phi. Y is rho sine theta sine phi. Z is rho cosine phi. Right? And then x squared plus y squared plus z squared is rho squared. So the z becomes rho cosine phi. Rho cosine phi. Conversion factor is rho squared sine phi d rho d theta d phi. Okay, so we have rho to the third. So 0 to 4, 0 to 2 pi, 0 to pi over 3, rho to the third, cosine phi, sine phi, d rho, d theta, d phi. So 1/4 rho to the fourth. So 1/4 rho to the fourth. Of course, the phi is constant. And I'm going to remember this also here. So to make this a little easier, remember sine 2t is 2 sine t cosine t. So remember this double angle or half angle or whatever angle formula. Okay, so I'm going to rewrite that as 1/2 sine 2 phi. So then rho equals 0 to rho equals 4 d theta d phi. Okay, so at 4, this is, so 4 to the 4th, so 4 to the 3rd, 64, which is us 32 sine 2 phi d theta d phi. There's no thetas, it's all just a constant in regard to theta, so just get 2 pi again. So 64 pi 0 to pi over 3 sine 2 phi d phi. Antiderivative sine 2 phi is negative 1/2 cosine 2 phi. So that's minus 32 equals minus 32 cosine 2 phi from 0 to pi over 3. So at pi over 3, so 2 pi over 3, cosine of 2 pi over 3 is negative 1/2, right? So negative 1/2, and then at 0 it's 1. 2 pi over 3. Pi over 3 is 60. And then 2 pi over 3 is 60 coming from the negative x-axis. So it's negative 1/2. So we got negative 3/2. So, and I lost my pi, didn't I? There's a pi missing. So minus 3/2 times minus 3/2. So that's 16. 16 times 3 is 48. So 48 pi altogether. Okay. Nice spherical coordinates. Let's see. 286. In the following exercises, find the volume of the solid E whose boundaries are given in rectangular coordinates. So apparently you need to change it into spherical coordinates. So in 286 right here, convert the integral this dz dy dx into an integral in spherical coordinates and evaluate. So again, 286 is this cone business. It's again the snow cone, I think. Yeah, it's the snow cone again. I think we already calculated that one. So 286. So let's just. So it's square root x squared plus y squared. 16 minus x squared minus y squared. Is that what it was? Yeah. And then minus. wait a minute. Minus 4? Oh, yeah, because apparently that's where these guys intersect. Yeah, so this is dz, dy, dx. No, this is dz, dx, dy. No, dz, dy, dx, of course. All right, so convert to spherical. So the region being described is minus 2 less than or equal to x less than or equal to 2 minus square root 4 minus y squared less than or equal to... Wait a minute. Did I put x? It's supposed to be x's. Those are x's. Minus 4 minus x squared less than or equal to y less than or equal to square root 4 minus x squared. And then x squared plus y squared less than or equal to z less than or equal to 16 minus x squared minus y squared. So this is again that cone, snow cone shape. You have the cone x squared plus y squared square root equals to z. So that's the 45-degree cone. The cone whose sides are 45 degrees. And then you've got the region stalk between the cone and the sphere of radius 4. And apparently those guys intersect. They intersect in the circle of radius 4. So it's again this shape. I think they've beaten on this shape enough. So this is 0 less than or equal to rho less than or equal to 4, 0 less than or equal to theta less than or equal to 2 pi, 0 less than or equal to phi less than or equal to 45 degrees. Right, because that angle is 45, so this angle is 45 as well. Whereas with that other problem, the angle here was 30, so the angle down here was 60. Remember, phi is measured from the positive z-axis declining downward. So then it's just the triple integral over e of 1. Right, because there's just a 1 here. There's no function other than the constant 1. So it's just the volume of that. And I think we did this exact thing in a previous problem, didn't we? Did we not? That was the one, the double solution. Was that it? Oh, well, it was a 1 here, not a 4. So, I mean, it's very similar to number 262. So then, so this is the same as number 262. So we did 262 in both cylindrical and spherical, which you could do here as well. All right, that was 286. 292. I think we need to do something over the whole sphere. We haven't... Okay. Too many just volume problems. Express the volume of the solid inside the sphere of radius 4 and outside the cylinder of radius 2. So this is actually something that you probably are familiar with. So if you take a piece of solid wooden ball or a plastic ball, solid plastic ball, and then you drill a hole through it all the way down, you get those those shapes. You which you often find with dining sets, right? You know, you have these things where you put your nice napkins, your nice cloth napkins through these balls, right? They're sometimes shaped like balls. They don't have to be. Sometimes they're just a cylindrical shell or something like that. But a lot of time it's a ball with a hole drilled through the middle. You know, a large hole, and you just pull your napkin through that, and you lay that on your place setting. So here they're asking you to find the volume of that thing. And so this is possibly something interesting to, well, maybe we need to move on to the last section. So let's just omit that. You know, you can do it on your own if, I think that's one's done more in cylindrical coordinates than spherical. Yeah, I would be doing it. Oh, I mean, you can do this. So describe, the region in spherical coordinates. Cylindrical coordinates. You can do it in spherical, but it's more complicated. The integral will be more complicated too. So essentially, you're just going to do like 1/8 of this thing. You have this sphere of radius 4, and you're going to drill out the cylinder of radius 2. And so that goes away, and you're just left with this red bit here. Right, so you would calculate 1/8 of the volume, and then multiply your answer by 8. This volume, and then multiply by 8. Right, for the napkin holder ball or something like that. Oh, another place you saw that, like my mom used to do macrame back in the 80s. She used to make these plant hangers, and those balls, wooden balls with the holes drilled out in the middle. That was like one of the little knickknacks you would put on these things as you were making them. So, all right. So moving on to section 5.6, just a couple problems in section 5.6. These are pretty long and involved ones, and actually the one on the syllabus number 306 is not doable really. It's another one of those omissions of these guys, but I'll replace it with something. Oh, sorry, next section. So centers of mass and moments of inertia. So we're just doing center of mass. We're not going to talk about moments of inertia right now, just the centers of mass. So number 298. So in the following exercises, the region R occupied by the lamina shown in the graph, lamina is like a flat, thin, flat thing. Find the mass of R with the density function given. So the density function here, rho is x plus y, and the triangular region has got coordinates 0, 0, 1, 1, and 0, 5. Right, so they stretched out the x-axis. Okay, so 298. So 5, 1, 1, and 0, 0. So here is, so that density function is x plus y. So remember, okay, that and then this region here, we'll call it E, or what do they call it, D? I was using different letters D and B and E and R. They're all just R. R for region. Anyway, so remember the mass. So the multiple integrals and single integrals, can represent geometric areas and then volumes and then a four-dimensional volume, whatever that is. So that's describing the one variable in 2 dimensions, a two-dimensional measure. The two variables, a three-dimensional measure. The two variables, a three-dimensional measure, area, volume, and the three variables, a four-dimensional measure. But that's not quite so intuitive. But they can all be described in terms of mass. If the function you're integrating is a density function, so this is density per unit area, then the mass is just the integral of density over the region. So mass is the integral of density. And you may say, well, what does it mean to have a negative density? Well, what does it mean to have a negative area? Right? It's just as sort of contrived as that. But it's one way to think of it. So the mass is the double integral of rho x, y, dA over r, or d. Right? And then for the center of mass, x bar is 1 over the mass, double integral over d, x, rho x, y, dA. And then the y-coordinate is 1 over the mass, double integral over d, y, rho x, y, dA. And then in 3 dimensions, it's the same thing, except you're going to have a z bar, but it's just the triple integral z, rho x, y, z. It's all very, it's all very clean, the formulas here. Right, and remember what those formulas represent. They represent total moments over total mass. It's all a generalization of Archimedes' lever law. So going all the way back to Archimedes, 100 BC or whatever it was when he was around, Archimedes' lever law, put into practice using integration, and it just pops out like this. So moments is x, coordinate, x coordinate times mass divided by total mass. So moments are coordinate times mass, right? And mass is density times area. So coordinate, x coordinates times mass divided by total mass. So it's total moments over total mass. Okay, so let's do it for this region here. So double integral over d of rho. Oh, so we have to describe d, don't we? So d, so what's this line? This is the line y equals x. And what's this line here? This is the line y equals slope x plus b, which is 5. And so what's the slope of this thing? So rise over run. So the rise is -4 over the run is 1. So -4. Minus 4x plus 5. Right? 5 minus 1 over 1. Over 1 minus 5 over 1 minus 0. Yeah, negative 4x plus 5. So d is equal to, z is less than or equal to x is less than or equal to 1. And then the y-coordinate is stuck between x and 5 minus 4x. So that's a type 1 description. All right, so the mass is double integral over d x plus y dA, which is x to 5 minus 4x, and then 0 to 1, x plus y dy dx. So, integral from 0 to 1 Antiderivative with regard to y is xy plus a half y squared from y equals x to y equals 5 minus 4x dx. So this is equal to, so x times 5 minus 4x minus x. Well, we'll do the whole thing. Plus 1/2 5 minus 4x squared minus x squared plus a half y squared is x to the 4th dx. That's going to be nasty. So x times 5 minus 4x plus 1/2 5 minus 4x squared x times 5 minus 4x plus 1/2 x times 5 minus 4x squared minus x squared minus 1/2 x to the 4th. So expand. So 1/2 x to the 4th plus 3x squared minus 15x plus 23x. So 1/2 x to the 4th plus 3x squared minus 15x plus 23 over 2 dx. Okay, so from integral with respect to x, so I have 1/10 x to the 5th plus x to the 3rd minus 15 halves x squared plus 23 over 2x from 0 to 1. So 1/10 plus 1 minus 15 halves plus 23 over 2. So 15 minus 23 is 8 over 2 is 4. Right? 23 minus 15 is 8 over 2 is 4. So plus 1 is 5. So 51 over 10. Seriously? So 5 plus a 10th, 5.1, I guess. Right, 5 plus a 10th, yeah, 5.1. So that's the mass. And then the x bar is, so 1 over 5.1 double integral over dx rho x, well, x times x plus y dA. So So that's 1 over 5.1 x to 5 minus 4x, 0 to 1, x squared plus xy y dx. And that is going to be, I mean, even worse. It is going to be even worse. That's a terrible problem. All right, well, 1 over 5.1, integral from 0 to 1, 1/3 x to the third plus 1/2 x y squared from x to 5 minus 4x. Or, I'm sorry, this is all with regard to y. X squared y plus 1/2 x y squared x to 5 minus 4x for y dx. So 1 over 5.1, integral from 0 to 1. So 5 minus 4x plus 1/2 x times 5 minus 4x squared minus x to the third plus 1/2 x to the third. Yeah, at x, this is x to the third plus 1/2 x to the third. Oh, did I did make a mistake up here, didn't I? This is x squared. There it is. 2.5 x squared minus 15x plus 12.5. Okay, should be a little better now. So 5/2 x squared minus 15x plus 23 over 5 dx. So that becomes 5/6 x to the third minus 15/2 x plus 23 x squared. 23 over 5x from 0 to 1. So this is equal to 5 over 6 minus 15 over 2 plus 23 over 5. And the the least common denominator of all of these is 30. So we have 25. And that's multiplied by 15. Minus 225 plus multiply by that by 6. 120 plus 18, 138. That's negative. Oh no, 15 squared. Yeah, 15 squared is 225, right? So 5/2 x squared minus 15 x plus 23 over 2. So 5/6, 15/2 23 over 5. 5 6 minus 15 halves plus 23 over 5. $225. What's going on here? Minus a half x squared x times 5 minus 4x plus 1 half 5 minus 4x squared minus x squared plus a half, so it's 3 halves x squared.
Dr. Salati, I think the 12.5 is 25 over 2, not 23 over 5.
Well, 25 over 2. No. That is it. So the least common denominator here is 6. So this is 5 minus 45 plus 50 over 6. That's 10 over 6. Right? 50 minus 45 is 5 plus 5 is 10 over 6. So that's 5/3. So this is then 3/5. All right, so now polynomial simplify the polynomial here. So x squared times 5 minus plus 1 half x times 5 minus 4x squared minus 3 halves x to the third. So 2.5 x to the third minus 15 x squared so minus 15x squared plus 25 over 2x dx. So 3/5 antiderivative, so 5/8 x to the fourth minus 5x to the third plus 25 over 4x squared from 0 to 1. So this gives me 3/5 times 5/8 minus 5 plus 25 over 4. So least common denominator here is 8. So 3/5 times 5 minus 40 plus 50 over 8. So 15 over 8. So that gives me 9 over 8. So that is the x bar, the 9/8. Which can't be right because it must be between 0 and 1, it would seem. And that is past the 1, so that can't be right. 9/8. x times x plus y x squared plus xy dy plus 1/2 xy squared, so x times 5 minus 4x squared times 5 minus 4x minus x to the third plus 1/2 x to the third, so it's 3/2 x to the third plus right here is plus. Right, since we're calculating a center of mass, we do have some intuition as to where this thing is supposed to be, right? Right, so we just got an answer of 9/8, but it can't be that, right? Because it has to be between 0 and 1, the center of mass for x. Is a little bit bigger, so 5.5 x to the third, so that's 11/2. So 11/2, 11/8, 11 over 8, so that's 11. Oh, but now it's even worse. No, it's minus 3/2. Oh, that was right. 3/2 minus 3/2. This is a plus 1/2. X squared times 5 minus 4x plus 1/2 x, 5 minus 4x squared, minus 3/2 x to the third. No, so 5/2 minus 15 plus 12.5. Three-fifths times 5/8. Well, 15/8. So that's a 3, so 9/8. X to the third, 1/2 x to the third, minus 3/2 x to the third. Minus x squared plus 1/2 x squared. So this is 5 minus 4x times x plus 5/2 minus 2x. So it's minus x. So 4x squared minus 5 plus 25 over 2. So 4x squared minus 15x plus 25 over 2. And then minus 3/2 x squared. So minus 1.5, so that's 3, so it's 2.5. That's what this is right here. 0 to 1, 5, 6, minus 15/2 plus 25/2. Multiplying by 3, oh. 75. Multiply by 3, this is 45, this is 75. So 75 minus 45 is negative 30, or sorry, it's 30 plus 5, so it's 35 over 6. So 35 over 6 is not divisible by any of those. So this is 6 over 35. This ought to fix it. Six over 35. 6 over 35. Of course, that's a much smaller number than what we had before. So this is bound to be less than 1. So 6 over 35 times 15 over 8 is some 9 over 28. Right, this is 3, this is 4, this is 3, this is 7, so 3/7 times 3/4, 9 over 28. Right, so, you know, we knew that answer was wrong because, I mean, the answer would be between 0 and 1. The center of mass of this thing here cannot be, so that so 9 over 28, so it's like, what, a third or something? Right, so it's right about there, the x bar. Okay. It certainly can't be out here. So then the y bar, hopefully this one's a little nicer, is 1 over the mass, double integral over d, y times x plus y dA. So 6 over 35, and again, this is x times 5 minus 4x, and then 0 to 1. Yx plus y squared dy dx. So this is equal to 6 over 35, and go from 0 to 1, 1/2 y squared x plus 1/3 y to the third from x to 5 minus 4x dx. So integral from 0 to 1, so 1/2 5 minus 4x squared times x plus 1/3 5 minus 4x to the third minus 1/2 x to the third plus 1/3 x to the third dx. Even worse. Oh. One half x times 5 minus 4x squared plus 1/3 5 minus 4x to the third minus, so a half plus a third is 5 over 6. 1/3 5 minus 4x to the third, 1/2 5 minus 4x squared times x. Okay. So integral x equals 0 to x equals 1 of that. 13.5583. Can I get him to do it in terms of, maybe if I put a 1/2 here. Not give me a decimal. 1627 over 120. So 1627 over 120. Times 6 over 35. 2.324. 3242. 2.3242. I mean, who are these guys kidding? So anyway, the answer makes sense, right? So the 9 over 28 is just a little bigger than 1/3. So this is, a little bigger than 1/3. So that's the X bar, and then the Y bar is 2.3. So about halfway down, a little bit more down. So actually this is 2. So it's like right here. Right, so that's the center of mass. Right, so that answer makes some sense, given the density function x plus y. The thing gets more dense the further you get away from the origin, so to speak. Right, but there's much more of this lamina here on the left than there is on the right. So even though it's like more dense here, the center of mass is still kind of, towards the left. Okay, so terrible problem. I'm very sorry about that. Let me mark that on the syllabus. Uh, 306 is the next one. That one is not doable. I already know that for a fact. Let's take a look at number, say, 300. Okay, so we got something a little bit like, more doable here. Okay, number 300. So number 300, and this is enough like practice for the exam. If you could do like 299, so do 299 on your own. And the answer's in the back of the book. 300, we'll do it here. And then we're going to omit the rest, 322 to 348. So 322 to 348, omit those. Okay, we're just going to do just a simple center of mass calculation. So for 302 or 300, we have this rectangle. So x goes from 0 to 3, y goes from 1 to 3. 0 is less than or equal to x is less than or equal to 3. 1 is less than or equal to y, less than or equal to 3. You've just got this rectangle. All right, and then you have this row function, xy squared, yeah? X squared y. All right, so find the center of mass. So the mass is the double integral over r x squared y dA. So, I mean, since it's a rectangle, life is definitely a little easier here. So 1 to 3 for y, 0 to 3 for x squared y dy dx. Antiderivative with regard to y is 1/2 x squared y squared from 1 to 3. So this is y equals 1, so y equals 3, of course. All right, so this is 9 minus 1 is 8. So it becomes 4, integral from 0 to 3, x squared dx. So 4/3 x to the third from 0 to 3. And so we get to 27, so 9 times 4 is 36. So the mass is 36, units. So x bar is 1 over 36, double integral, x to the third. Well, it's x times x squared y dA over r. So 1 over 36. 1 to 3, 0 to 3, x to the third y dy dx. So 1 over 36, 1/2 x to the third y squared from 1 to 3. So 9 minus 1 is 8 again. 8 over 2 is 4, so it's 4 over 36. So 4 over 36, 1/9, of course. X to the third dx from 0 to 3. So 1/4. So it becomes 1/4. So just 1 over 36. X to the fourth from 0 to 3. 3 to the fourth is 81. So 81 over 36, right? They're both divisible by 9. So 9 over 4. So 9 over 4 is 2.1 for x bar. Oh, I didn't draw the triangle. So, so the x goes from 0 to 3. So it's out towards the right, right? X goes from 0 to 3. So 0 to 3. So 2.1 is like there. Right, but of course the thing gets more dense as you go in the x direction, x squared y. So it makes sense that the x bar is well off to the right there. It gets a lot more dense as you go further along the x-axis because it's an x squared here. So it's not going to go as far. 1, 0, 1, 3, 1, 3, 3. 0, 3. It's not going to go quite as far in the y direction. So from 1 to 3, just a little bit more than halfway. So it'll be 2.1 or something like that again. So the y bar (1 over) what was the mass again? 36. 1 over 36. Double integral y times x squared y dA over r. So 1 over 36, integral from 1 to 3, 0 to 3, x squared y squared dy dx. So this is equal to 1 over 36, 1/3 x squared y to the third from 1 to 3. So what is this? 27 minus 1 is 26. So we have 26 over 3 times 36. Right. 26 over 3 times 36. Integral from 0 to 3. X to the third dx. So 1/4. So 26 over 3 times 36 times 4, x to the fourth, no, 27, I changed my square into a third. So it's 1/3. 26 over 9 times 36, x to the third from 0 to 3. So then that's 26 times 27 over 9 times 36. So 26 times 27 divided by 9 times 36. So 13 over 6. So the y bar is 2.2 and a sixth. All right, so just a little bit past 2. All right, so here's the x bar is 9 over 4. And y bar is 13 over 6. So it's 2 and a sixth. So here's the x bar, y bar. All right, so that's your center of mass for this thing, and you know that makes intuitive sense. Makes intuitive sense what that what that center of mass is. Okay. So all I'm looking for in this section is that we know the center of mass formulae. Okay. Mass is the double integral for 2 dimensions. Mass is the double integral of density over the region. Where did that go? Mass is the double integral of density. Right? X bar is 1 over the mass times the double integral of x times density. Total moments over total mass. Right? And integration, of course, is the sum. Right? So the sum of the total moments over the total mass. And the sum of the total y moments over the total mass for y bar. Right? So number 298 is a nasty problem, but number 300 is definitely like, that's the kind of thing you could see on an exam, right? You have this rectangle, you get this density function on a rectangle. I like these problems when the density is 1, actually. Because like then you look at these geometric objects and you can find the center of mass for these geometric objects where the density is 1, and your intuition really tells you like where that center of mass should be. So you get this nice intuitive check on your calculations. But these problems are good as well. Okay. So that's it. That's all the material. Again, it's not as much as what was on the other exams, but we're going to start next time with some review, and I'm available from 11:30 to 12:30. Oh, that was this morning. I'm sorry. If you want to meet with me, during some time outside of class, send me an email and we'll arrange something if you need some extra help, okay? Other than that, just work on these problems, work these problems that we worked, work them on your own and check your answers against mine, and, that should be sufficient preparation for you, okay? All right, have a nice night and have a good holiday, and